discuss matrices. So we're going to be picking up here with completing Module 3, looking at matrices. So I'm going to start sharing my screen. All right, I'm going to pull up the notes here first. Let's talk about it a little bit. All right, so from this current slide, remember the very first part of this section, we were talking about applications with exponential functions, and then now we're going to begin looking at matrices. All right, so matrices are used to display information and to solve systems of linear equations. A matrix, plural matrices, is a rectangular array. The information is arranged in rows and columns and placed in brackets. The values inside the brackets are called the elements of the matrix. Here's an example. The numbers within, generic, just numbers 1, 2, 3, and 4 are the elements of the matrix. Okay. You can actually name a matrix by a capital letter, such as matrix A, matrix B, matrix C. And you can also name it using a lowercase letter enclosed within brackets to denote it. And the IJ, the little subtext IJ, just refers to the number of I would actually not really recommend naming it that way. We actually name, no, we can name it that way. I and J just representing the number of rows and columns that you have. And you always name a matrix by the rows first, then the columns. So I represents number of rows, J represents the number of columns. Now, if you leave off the bracket, then you can actually name or give just a general element within the matrix is denoted by just AIJ. This references the element in the ith row and jth column when you actually leave off the actual bracket. So a matrix of order m by n has m rows and n columns. Again, you always name it by the rows first. So if a matrix has the same number of rows and columns, it is said to be a square matrix. The first step in solving a system of linear equations when we're using matrices is to write the augmented matrix. An augmented matrix has a vertical bar that separates the columns of the matrix into two groups. The coefficients of each variable are placed to the left of the vertical line or vertical bar, and the constants are placed to the right. So you can almost think of the vertical bar as if it's acting as your equal sign. Any variable that is missing would have a coefficient of 0. So let's take a look at this. So here's the system, the two systems here on the left side. As you can see, we've got them in their standard form where the variables are on the left and their respective coefficients in front, and then equal to the constants here on the right. So that first row is 3x plus y plus 2z equals 31. It would be the first row in the matrix, the coefficients of it, 3, 1, 2, and then on the right side of the bar is the constant 31. So you can almost treat the bar, the vertical bar, as the equal sign, separating the coefficients from the constants. Same thing here with the second row, coefficient 1, 1, 2, and then equal to your constant 19. And then the third row, 1, 3, 2, equal to the constant 25. Now look at this second matrix here, or the second system of equations. So each one of these systems has or involves three variables, and we can see that because that first equation, even here with this second system, that first equation does show variables x, y, and z, even though the second equation shows only two variables and the third equation shows only one variable. This is a system still in three variables. We would just have to show that the second equation is missing the variable x. So that means its coefficient, because it's missing, its coefficient is understood to be 0. So we place a 0 in for that missing coefficient. And then that third equation is missing both x and y. So we put in zeros for each one of those coefficients in their place. So you've got the first equation represented here by the first row. 1, 2, -5 are the coefficients, and then equal to 19 here on the right side. The second row, 0, 1, 3, equal to 9. And then the third row, 0, 0, 1, the coefficients 0, 0, and then the coefficient in front of z is understood to be a 1, 0, 0, 1, and then equal to 4. So when we look at this first example here, it says write the augmented matrix for the system of linear equations. You replace the missing variables with zeros. And then you, again, for each row, you have a row, or for each system, each equation of the system, you have it represented by a row in the matrix. Again, keeping the constants here on the right side of the bar and the coefficients on the left. Okay? We can do that also in our homework. Let's take a look at an example from the homework. So here we've got on example number 5, the first start of the homework that begins with matrices is at number 5. The previous 4 questions were related to the exponential equations, word problems, or related to exponentials. So number 5, it says write the augmented matrix for the system of linear equations. So as you can see, the bar is understood to be there, or it's shown here. Sometimes it's shown, sometimes it's not, but we do actually see it here. Then you've got already shown for us. Then you've got the first equation. So let's put the coefficients here and then equal to the constant. So -9, -1, -1, 1. So -9 is the coefficient for W, -1, -1, and then +1, equal to -23. Second equation, you are missing the W, so I'm going to put a 0 there. So we've got 0W, so we got 0. You've got 2 as the coefficient for x. So remember, this is W because we're lining these up. W, X, Y, Z. W, X, Y, Z. Coefficients in front of W, coefficients in front of the X's, coefficients in front of the Y's, coefficients in front of the Z's, if that helps to label that. So we've got 0, 2, 1, and the Z is missing here, so another 0, and then 14. The third equation, 1, 1, 6, 0, and then 31. And then the last one, 6, -5, -4, 0, and then -29. Okay? So just like with this one, this number 5, we were able to take the system and write it as an augmented matrix. We can go in the opposite direction as well on number 6, where they're giving us the matrix and we're asked to work in reverse and write the system. So this says on number 6, write the system of linear equations represented by the augmented matrix to the right. So I'm going to take this matrix, I'm going to call this equation 1, equation 2, equation 3. When you're taking the system, keep in mind the values to the left of the bar represent your coefficients, and your variables We're told to use X, Y, and Z. Your variables are in alphabetical order. So X, coefficients, Y, coefficients, Z, and then here you have your constants. So that first equation would give us 6x plus 0y plus 5z equals negative 10. And of course, when you have a zero coefficient, there's no reason to show it. So we're going to just drop that off. 6x plus 5z equals negative 10. The second equation, we've got 0x plus 1y minus 2z equals 11. Again, no need to show the zero. So we've got 1y, so just y, minus 2z equals 11. And then the third equation, we've got 8x plus 7y plus 0z equals 4. So 8x plus 7y equals 4. Okay? All right. Let's go back to the notes here. We'll move on from that one. Okay. So I want to discuss row operations, but I want to stress to you that this is something that you won't have to do by hand, okay? This is where the calculator is going to be very useful, very important, because if you had to solve a system using row operations, it could get very involved. It could get a little lengthy. And so you're not asked to do row operations at all in the assignments, but I cannot show you how to use the calculator without kind of explaining where it comes from, okay? So let's just kind of talk about row operations because it's going to lead us into solving systems using matrices. So a matrix with ones shown on the main diagonal and zeros below the ones is said to be in row echelon form. We use row operations on the augmented matrix to produce a matrix in row echelon form. So here's an example of row echelon. You've got a main diagonal of ones and zeros below, okay? The main diagonal has ones, and you've got zeros below below the ones in the main diagonal. So this is said to be in row echelon form. The following row operations produce matrices that represent systems with the same solution set. So in other words, you can perform row operations to get equivalent systems, okay, that they're equivalent because they end up having the same solution set. So it allows you to reduce it down, which is why it's kind of called row echelon. We'll talk about that. Reducing it down to a more simplified form that's still equivalent because they still represent the same solution set. So two rows of a matrix may be interchanged. You can swap rows out, in other words. This is the same as interchanging two equations in a linear system. The elements in any row may be multiplied by a non-zero number. This is the same as multiplying both sides of an equation by a non-zero number. And then thirdly, the elements in any row can be multiplied by a non-zero number. These products can then be added to the corresponding elements in any other row. So first, when you think about interchanging two rows, it's just, again, just swapping the two rows out, multiplying each element in a row by some scalar factor k, and adding k times the elements in row I, let's say, to the corresponding elements in another row j. So I want to show you just how it kind of looks, But this is what would be done before we had calculators, before we had technology that could do the operations for us. We would have to take this matrix and perform row operations so that we could then end up getting ones in the main diagonal and zeros below so that we could somehow get the solution set to a system using matrices. So here it says perform the indicated row operation. This is just where you're swapping or switching row 1 and row 2. So where row 1 was, it gets moved to row 2. They're just swapped. So this now becomes row 1. That second row here is now the top row, first row, and then first row here now is the second row. You can actually, again, multiply a row by some scalar factor. We're multiplying, it says row 1 by 1/4. So that is where we take each element of row 1 and multiply it by 1/4. This would yield a 1 in that top main diagonal, which would be important if we were trying to put this matrix in row echelon form so that we could solve it. It would be important that we got ones in that main diagonal. Here is an example where you're multiplying 3 by row 2, and then we're going to end up adding that new row. Once we multiply 3 by every element in that second row, we'll then add it to row 3. Okay, and when we add it to row 3, that becomes 0 here, 16, -8, 12. So when you're solving a system using matrices, it's called Gaussian elimination method. On the calculator, that is essentially getting a reduced row echelon form. Okay? We'll talk about it in more detail here in just a second, but solving linear systems of 3 equations with 3 variables using Gaussian elimination. You would first write the augmented matrix for the system, and then you would use row operations to simplify the matrix to a row equivalent matrix in row echelon form. Row echelon form is where you have ones down the main diagonal and zeros underneath or below the ones. The numbers above are not important in row echelon form because what you'll do is you'll take each new equation that you have in this row echelon form, and you may have to do some back substitution to get the actual solutions. But taking the original matrix, its augmented matrix, and putting it in row echelon form allows us to then solve for the system. Now, this is if you had to do it by hand, you would actually be performing row operations. But guess what? We've got the calculator. So it says solving linear systems using Gauss-Jordan elimination. Okay. So it says use matrix, write the augmented matrix first, and then use matrix row operations to simplify the matrix to a row equivalent matrix and reduce row echelon form. So I'm going to show you here, but then I'm going to show you on the calculator. So the first thing we need to do is get ones in the main diagonal and then zeros below it. Okay, so I'm just kind of getting through here so you can kind of see. So take a look at this system. Here's the system, and we're told to use Gauss-Jordan elimination. So that means once we put the system in the augmented matrix, then we actually simplify it down using row operations, and it gives us this. Okay, when we solve this system using Gaussian elimination with back substitution, we simplified the system to this matrix, and then we'll begin to work from this step. So this step right here, keep in mind, I did not show you the row operation steps because I'm going to let the calculator do it for us. But I want you to see what happens once you actually get to this form from the calculator, how you'll then solve and get the solutions of X, Y, and Z for the system. And then, of course, we're going to do some homework problems. So if you're using Gauss-Jordan elimination, then you still have some work to do as far as getting the zeros up here as well. There's a method called Gaussian elimination, and then there's Gauss-Jordan. Gaussian elimination gets you to this one. It's where you got the ones in the main diagonal. This is Gaussian, and you got zeros below. Gauss-Jordan is where you take it even a step further and you get zeros above the main diagonal as well. That's Gauss-Jordan. That's when you put it in its simplest form possible. And again, they're showing you more operations. This is showing you more operations. So you're taking the original matrix, putting it in Gaussian form, and then going all the way even simpler to the Gauss-Jordan form. That is where you got ones in the main diagonal, zeros below, and zeros above. Because what happens here is when you get it in this form right here, then you're able to say that each one of these ones represents a coefficient. Remember, in alphabetical order, these coefficients represent x, these represent the y, these represent the z coefficients. So this would be 1x, you got 0y and 0z, so this would be 1x equals 5, or simply x equals 5. The second equation, the second row, you got 0x, 1y, 0z. So you end up with, and then equals 2. So you end up with just 1y equals 2, or simply y equals 2. And then the third equation, you got 0x, 0y, you got 1z equals 3, or simply z equals 3. So this last matrix, once it's in Gauss-Jordan form, where you've got ones in the main diagonal and zeros below and zeros above, this last simple matrix can show you your solution set. Now you might be wondering, well, what can I do to not have to do all that work? I'm glad you asked. We're going to use our calculators. Using technology to bypass steps in Gauss-Jordan elimination method, we will use our calculators to perform Gauss-Jordan elimination to find solutions of systems. Steps for entering in calculator, I'm going to talk about right now. Okay, so let's go back here. So I'm going to minimize this, and we're going to go right into a homework problem. So let's do number 7. Let's get to it. Now it says Gaussian elimination, and that means you would have to also then do some back substitution. I'm going to eliminate that work for you. We're going to use Gauss-Jordan, and that way you don't have to do any back substitution. We're going to use Gauss-Jordan. So basically, the mathematician Gaussian came up with the elimination method initially, and then he hooked up with another mathematician, namely Jordan, and they simplified it even further. So Gauss-Jordan elimination is what we're going to use. On your calculator, this is known as reduced row echelon form, RREF. Gaussian elimination is known as just REF, reduced echelon form. Row echelon form. Row echelon form. Gauss-Jordan is known as reduced row echelon form. So it'll be the 2 R's, okay? So let's jump into this. Let me get some paper here. I may not have enough room. And let's do it. So number 7, the first thing I'm going to do is I'm going to write it as an augmented matrix. That way I know exactly how to put this into my calculator. Sorry about that. It's kind of blurry a little bit, isn't it? Okay, I may have to zoom out a bit. So the first thing I'm going to do is recognize that this becomes my augmented matrix on number 7, 1, 1, -1. -5, 5, -1, 1, -1, -1, 4, -3, 1. Okay? And I apologize if y'all hear any background noise. A little bit noisy here. So we're going to put this in our calculator. We're going to pull up matrices. And as you can see on my calculator here, scoot it up so you can see it a bit better. You've got matrix as the second function of this x1 key, or x to the negative first key. So I am going to, let's turn it on here. I'm going to press second x inverse key. Now, the first thing I have to do is edit. So let's make sure we know what size matrix we have. Remember, your size of your matrix is named rows by columns. So this is a 1, 2, 3 rows by 1, 2, 3, 4 columns. Okay. Now, I will say this, when I put this on my calculator, I won't see the bar. So you kind of have to understand that it's invisible on your calculator, okay? It's understood to be there. So let's go over to edit, and I'm going to just edit the first one, and this is a 3 by 4, okay? So I'm going to go across. It makes me go across when I enter them in. So I press 1, enter, 1, enter, -1. Just press enter after each element. Then it takes me to the next row. 5, -1, 1, -1, then -1. Uh-oh. Let's go back there. 4, -3, 1. Okay? So 1, 1, -1, -5, 5, -1, 1, -1, -1, 4, -3, 1. So again, the bar is not shown, but it's understood to be there, okay? I'm acting as if it's there. Now, when I'm done editing, please make sure when you're done editing that you get out of the matrix, because you don't want to perform any operations while you're still inside edit. So to get out of the edit screen, press second mode, which is just the quit, okay? And that just takes you back to your home screen. And from your home screen is where you want to perform your work. So what we want to do is then perform RREF, reduced row echelon form, on this matrix. So I'm going to go back to the matrix again, press second X inverse, and this time I'm going to math because I want to actually choose what I want to do. And I'm going to scroll down until I see RREF. Now look, A is REF. That is row echelon form. That one, A, won't give you the most reduced form. It will give you the form where you have to then do the back substitution. So that's more Gaussian. That's the Gaussian method. We want to select the RREF because it puts the matrix in the lowest form possible, the most reduced form. So I'm selecting B, and it puts that on the home screen. And then I need to tell the calculator which matrix to use or which matrix to perform this on. Okay. So I'm going to then press second matrix again. And remember, I put it in A. A is the actual only one with anything in it anyway. So names is darkened, and one is kind of highlighted or darkened, but I haven't chosen until I press enter. And so it's going to perform reduced row echelon form on matrix A. So I'm going to press enter, and there it is. So I'm going to put equals here, or put an arrow here, and I'm going to write this down so that we can then identify our solutions. So we got 1, 0, 0, and then -1, 0, 1, 0, 12, 0, 0, 1, 16. Okay, so remember, the line is not shown, but we understand it to be there, okay? So I've got reduced row echelon form, because I've got ones in the main diagonals, I've got zeros below and zeros above. So I've got the coefficient for X, the coefficient for Y, the coefficient for Z. I've got a row for or column for each one. So notice in that first row, I only have a 1 for X, 0Y, 0Z. So I've got 1X equals -1, which in turn just means X equals -1. The second equation, I have 0X and 0Z. So I've got 1Y equals 12, or simply Y equals 12. And then the third row, I've got 0x and 0y. I've got 1z equals 16, or simply z equals 16. So my ordered solution set, my solution set is -1, 12, 16. The solution for x, for y, for z. Okay? All right. Let's do another one. Number 8. So again, it says solve the system of equations using matrices, and it says use the Gaussian elimination method with back substitution. There is no reason to make you do back substitution if you don't have to, okay? There's no reason. I want to show you, though, just briefly what it's referencing so you can kind of gauge what I'm talking about. What I might do, yeah, we'll do it. Look at number 8. So for number 8, I'm going to put the matrix again in the calculator. I'm going to put it in matrix A again. So I'm going to press second matrix, and I'm going to select A again because it's the same 1, 2, 3 rows, 1, 2, 3, 4. So I'm going to go over and edit it though. It's still 3 by 4, so I don't want to change the size. So I'm going to keep that, just press enter until I get down here to the elements. So I'm going to type over these elements. 4, 4, 16, 8, 4, 3, 12, 6, 4, 7, 23, 19. Okay? So we've got our elements entered in, our coefficients, and our constants here. I want to show you Gaussian elimination, the difference that would require some back substitution. Okay, I want to show you. And I'm going to show you the Gauss-Jordan elimination method, what we did here on the previous problem. So I'm done editing. So remember, you always remove or get out of this matrix. You don't want to be in the edit screen when you're starting to do the actual calculations. So press second mode to get out of that. All right, I'm going to clear all that off. That's from a previous problem. Now, let's go back to the matrix, and let's select the math. And we're going to go down. I want you to see something here. Let's suppose I select the row echelon form. Let's select A. And then I'm going to actually tell the calculator where my matrix is located. It's in A. Okay, so it's going to perform row echelon form on matrix A. And it gives me some decimals, which I don't want. So let's press math. Let's see if it'll do it for us. Yeah. Excuse me. So we press math. We do that again. I think I went through it a little fast. We press math, and then we went frac. And what it did was it took the previous answer, that matrix, and it put the values in fraction form instead of decimals. Excuse me. So as you can see, these equations here that would be formed from each of these rows would require some extra work, okay? Let me show you. That bottom equation, or even if we started with the top equation, it would be 1x plus 1y plus 4z equals 2. The second equation would be, there's no x, it would be 1y plus 7/3 z equals 11/3. And then that third equation, it's 1z equals -1. So z is the only solution that you currently have right now. what we would have to do is use back substitution to plug this in, let's say in here, to then finally get the y. So let's say we substitute, that's why it's called back substitute. So you're taking that last equation and you're back substituting it into the equation before it to get the y. And then you're going to take both the z value and the y that you're going to get and back substitute those in here into the first equation in order to get the x. So yes, you'll eventually get to the solution, but it takes you a little bit more work because the matrix wasn't in the most reduced form. Okay, so back substitute into second equation, excuse me, second equation to get y. Okay, please excuse me. Okay, so it would take a bit more work when you don't have to do the work. So rather than do that, why not just go all the way down to reduced row echelon form and get the actual solutions for X, Y, and Z up front, okay? Rather than having to go, for example, if I use back substitution, I would plug in this Z, which is -1, and then I would solve this, which would be y minus 7/3 equals 11/3. And then I would add 7/3. And so 11 plus 7, 18 over 3, 18/3, which would be 6. So I would finally get the value of y, and I have z. Then I would take each of those and plug those in here into the first equation to finally get the x. So it would take a little bit more work. Why not just let the calculator do it all for you? So that's what we're going to do. So I'm going to go back to number 8, the same problem I just used, the REF. I'm going to use RREF. So let's go back here. We already have the matrix entered in. Remember, we already put it in. So what we're going to do is just then go second matrix, and we're going to go math, and we're going to pull up the RREFB right here, select it, and then select which matrix we're performing it on. And we're using A. And there are solutions. 1x equals 0, 1y equals 6, 1z equals -1. So our solutions are 0, 6, -1. The value that x is equal to, the value that y is equal to, the value that z is equal to. Okay? So Gaussian elimination is unnecessary. Unnecessary. Gauss-Jordan is what we're using, which on the calculator is referred to RREF. Okay? All right, let's move on here. Let's see what else. Number 9 is asking us to determine the values of x and y that make the matrix true. So let's talk about that a little bit when we know equations or when we know matrices are true. So equality of matrices, let's see. So two matrices are equal if and only if they have the same order and corresponding elements are equal. So again, they will be equal if they have the same order, same size, basically, and the same corresponding elements. The definition of equality of matrices: two matrices A and B are equal if and only if they have the same order, m by n, and the same elements are equal. when you are, and we're going to look at an example, when you are dealing with matrices that have the same order, you can perform some matrix operations. You can add and you can subtract. So when you are adding matrices, you will just simply add the corresponding elements. You will add the elements in the corresponding positions. When you are subtracting, you will simply subtract the elements in the corresponding positions. So we're going to look at a couple examples that relate to matrices that are equal or equal matrices and adding and subtracting. Let's go here to our examples. So let's look at number 9. It says determine the values of x and y that make the matrix equation true. Well, the good thing here is that both of these matrices are of the same size. So this one is a 2 by 1, and so is this one a 2 by 1. And they're placed equal to each other, which means their corresponding elements are equal. So the first element here is equal to the first element here. So x equals 3. And the first element in this second row is equal to this first element here in this second row. -7 equals y, or y equals -7. Okay? Let's look at another one here. May have to do a little bit more work on this one, but let's look at it. So number 10, find values for the variables so that the following matrices are equal. So here we've got a 2 by 2 equal to a 2 by 2. So top left element should equal the top left element in the other one. So you've got x in that top element here, this top spot, and here 11 in the top spot on this one. So x equals 11. Here you've got 5y in this top right position equal to 5. So 5y equals 5. And then z equals 3. And then 15 equals 15. So there's nothing to do with that one. So this one, x equals 11, we've got just x equals 11. Z equals 3, we got that. Only one little extra step here to do, divide by 5. 5y equals 5, so y equals 1. Okay? Number 11 is asking us to add a and b, subtract a and b, multiply a by 5, and then D, multiply A by -3, and then add to it 3 multiplied to matrix B. So let me explain what these two mean. We talked about these two just briefly here. We can add and subtract matrices that are of the same size. It would just be where we add or subtract their corresponding elements. So for example, this row 1, column 1 element, because it's in the row 1 and it's in column 1, will add to the row 1, column 1 element here in B. 1 plus 15, so that would be 16. Here, 12 plus 13, 25. 0 plus 10, 10. So when we're adding the two matrices here, we're just simply adding the corresponding elements. Okay. Similarly, when we're subtracting, we'll simply subtract the corresponding elements. And keep in mind, we can do this on our calculator as well. Okay. We can edit them in. It might be quicker or just as quick to just add and subtract them, but we can let the calculator do it for us. So totally up to you which way you want to go with that. When you're multiplying by a constant, this is just multiplying by a constant factor or a constant scalar, you're just going to be multiplying every element of that matrix by 5, by whatever number that is. So 5a means we multiply each of these elements by 5. So 5 times 1, that would be 5. 5 times 12, 72. 5 times 0, or actually that would be 5 times 12. Is that 60? Yeah, 60. 5 times 0, 0, 5 times 14, multiplying every element by 5. Now for this one, you would take A and multiply every element by -3. Then take B, multiply every element by +3. And then those two new matrices you add together. Okay? So this one I would probably definitely let the calculator do for me. Not because it's hard, but because it would just eliminate some of the work time. So I'm going to put these in the calculator if that's okay with you guys. I'm going to put in, by pressing second matrix, I'm going to put this in for A, of course, because it's called A. And this is a 1, 2, 3 rows by 1, 2, 3 columns. Okay. And this is a 1, 2, 3 by 3 also. Okay. So I'm going to enter these in. All right. So I'm going to put these in. Let's edit. Let's go over to edit. This is a 3 by 3. So I had to change the size right there. Okay. Scoot it over a bit. So this is A that I'm putting in. So 1, 12, 0, 14, -8, 10, -2, 11, -13. Okay, so that's A. I'm done with A. Then I get out of A. Let's go second quit, and let's go back to it again. And I'm going to edit B. I go down to B and then over to edit. Well, actually, I should have gone over to edit and then down to B. And B is also a 3 by 3. 3, enter, 3, enter. And so that's 15 going across, 13, 10, 13, -13, -10. Last row here, 0, 13, 9. Okay? All right. So once we're done with that, now we're ready to do whatever work they're asking us to do. So for part A, we're going to add them together. So I'm going to get out of this again, and I'm going to press second mode. I'm going to press second mode to get out of that, to go to the home screen. And now I'm ready to do part A. So I want to add A plus B. So let's press second matrix again. It's kind of repetitive going back and forth to that, but this is what we're doing when we're using a calculator, okay? Let me zoom out just a bit. Okay. And the glare, trying to see how I can get out this glare. Okay. All right, so I'm going to select A, and then I'm going to say plus, and I'm going to press second matrix again and select B. So there is the first part where I'm adding the elements together. 16, 27, -2, 25, -21, 24, 10, 0, -4. Okay? All right, part B wants us to subtract those. So I'm going to do the exact same thing again. Trying to get out this glare, you guys. Ugh, so bright. Okay, let's put it over here maybe. So I'm going to now press second matrix, select A, press the minus key. And when I say minus, I'm just using the minus key. And then second matrix, select B. So this was A plus B. This is now going to be A minus B. There we have it. -14, -1, -10. So you just select right here and you'll enter -14, 1, -2, -1, 5, -2, -10, 20, -22. Okay. Part C, you're trying to multiply 5A. Okay, so let's type that in. Let's type 5. Let's type 5. And then second matrix to select A. Okay, so again, it's just where we multiplied every element by 5. Okay, so I'll write that 5, 70, -10, 60, -40, 55, 0, 50, -65. Okay, and then almost done. Lastly here, part D, we are going to take -3 times A plus 3 times B. So I'm literally going to type that in exactly as I see it. -3, second matrix, select A, and then say plus 3, second matrix, and select B. And again, as long as you put the matrices in correctly, this will give you the right answer. -3 times A plus 3 times B. And there we have it. 42, 3, 30, -3, -15, -60, 6, 6, and 66. Okay? All right. Let's take a look at something else now. And here I just have a couple of examples in the notes that that were sent out to you last week, where you can actually see me adding the corresponding elements. So you can do this by hand, or again, you can do it in the calculator. If I was putting this in the calculator, I would call this matrix A, I would call this matrix B. Okay, and this would be a 2 by 2 because it's 2 rows by 2 columns, and this would be a 2 by 2. Same thing with the subtracting. This is a 3 by 2. 3 rows, 2 columns. And this is a 3 by 2. Remember, in order to add and subtract, they need to be the same size, because you have to be able to add or subtract the corresponding elements. Okay, so just some properties of matrix addition. Commutative property applies, meaning it doesn't matter the order that you add. A plus B is still B plus A. Okay. And then the associative property, if you're adding 3 matrices, it will still be the same. If you add the first 2 together, then the last one, or if you add the last 2 matrices together, then add to the first, and you're still going to get the same answer because you're just adding. And then here, of course, when you're adding 0, it's still just A. And then when they have opposites or their inverses, you end up with 0. Scalar multiplication, again, we looked at that. It's just where you're multiplying every element of the matrix by a constant. There you've got an example. Multiply each element by -6. There's your answer. And then this is an example here. You can see it worked out by hand, or like I just worked it out using the calculator. Multiplying every element of A by a 3, and then multiplying each element in B by 2. And then adding those values together, the corresponding elements together. So getting the new numbers first when you multiply, and then adding the corresponding elements. All right. Matrix multiplication is a bit different, okay? So here, let's suppose we think of it with a 2 by 2 first. So multiplying two by 2 matrices. They have 2 columns, they have 2 rows, okay? A and B. So here you would take the rows of the rows of matrix A, and you multiply it by the columns in B. Let me show you what I mean here. So we would take, so first off, this is a 2 by 2. I almost want to show you this using, yeah, let me go back here. Okay, so we take, let's say we want to fill this first position. So first off, this is a 2 by 2. The number of, I need to show you this on paper. Let me exit out of that for a second. It's going to be kind of hard to explain that without doing a little bit of writing. So let me get some paper here. So let's suppose we're trying to multiply matrices, and we have this 2 by 2 that's on my screen right now. Okay, I'm going to kind of move it out the way here. And I'm going to just write it down. So let's say we have A, B, and it was A, B, C, D, and then E, F, G, H. Okay. So this is a 2 by 2, 2 rows by 2 columns, and this is a 2 by 2. First off, in order to be able to multiply matrices, let me let this straighten out a little bit. I don't know why it's blurry like this. Stop doing that. Okay. Oh, come on. Okay. In order to be able to multiply matrices together, the rows, let me start off with this one. The columns of the first matrix, A being the first matrix, this is A, this is B. The columns of the first matrix need to match the rows of the second. They must match. Okay? If these are different, you cannot multiply them together. Okay? And the calculator, if you try to do it in the calculator and they don't match, the calculator will tell you error misdimension. So the columns of the first matrix, that's why order matters when you're multiplying. It doesn't matter when you're adding and subtracting. Well, it doesn't matter when you're adding, but it does when you're multiplying. So the columns of the first matrix must match the rows of the second matrix. Then, to get the size of our new matrix that we're going to form when we get the product, it will be this 2 by 2. This is the new size of the product. It will be whatever the rows are here and the columns are here. So the inside two numbers have to match, and the size of the new one will be a 2 by 2. So this will be a 2 by 2, meaning you'll have one spot here, one spot here, one here, and one here. Now, how do you get those values? Just like we got the size by using the rows of the first one and the columns of the second one, that's exactly how we're going to get the elements. We're going to say the rows here times the columns. So for this first spot, this is row 1 times column 1. Row 1, column 1. So it will be A times E plus B times G. The row times the column to get that first position. First element times first element plus second element times second element. Or if you have more, third element times third element. But it's the row times the column. You always use the rows of the first one, columns of the second. So for this one, this would still be row 1, but it's column 2. So it would be AB times FH. So A times F, first element times first element, plus B times H. Then here, this second row, this is row 2, column 1. So row 2, column 1. So this would be row 2, column 1. So C times E plus D times G. And in this element here is found by using row 2, column 2. So C times F plus D times H. So I wanted to actually explain or show you how we get those elements, okay? So that way when you're looking at this, because it really wasn't necessarily clear where these letters, all this combination was coming from. Even though I do have it here, it says row 1 of A times column 1 of B. I wanted you to see it, okay? Now, you can do this on the calculator as well. You do not have to do this by hand, but I wanted you to see how it's found, because sometimes if they don't have those matching dimensions, if the columns of the first one don't match the rows of the second, then you can't multiply them and the calculator will tell you error. So let's take a look at an example here, and then we'll look at it on the calculator as well. So here it says find AB, given that A is a 2 by 2 with 1, 3, 2, 5 as the elements, and B is also 2 by 2 with 4, 6, 1, 0 with its elements. So multiplying them together, they do have the same columns on A, has the same number of rows on B, and so this is a 2 by 2. The answer would be a 2 by 2. So we take for this first position, we take the first row times the first column. So 1 times 4 plus 3 times 1. Here, this position is the first row, second column. 1 times 6 plus 3 times 0. 1 times 6, 3 times 0. This is the, excuse me, this is the second row. This is the second row times the first column. 2 times 4 plus 5 times 1. And this is the second row times the second column. 2 times 6 plus 5 times 0. Okay? Simplifying that, adding, multiplying, then adding together here, we get 7, 6, 13, 12. So this is just what I just described in my little makeshift example here on my paper. The product of an M by N and an N by P. Notice that the N here is the column, the N here is the row, but it's the same. It will end up being an M by P. The number of rows you have on A and the number of columns you have on B will give you the size of the product. Okay? And you take the rows of the first one and you multiply them by the corresponding elements of the columns for the second one. And for the product of two matrices to be defined, the number of columns for the first matrix must equal the number of rows of the second matrix. Here's an example. If possible, find the product. Now this is a 2 by 2 and this is a 2 by 4. So yes, you can multiply these. It's going to be a bigger matrix, but the number of columns here matches the number of rows here. So it ends up being a 2 by 4. The final product would be a 2 by 4. Now, most definitely this one, how big it is, I would put this in the calculator. It would save so much work, okay? And literally, I would call this one matrix A, and I would call this one matrix B, and I would get my answer from the calculator A times B. Look at this one. This is a 2 by 4 times a 2 by 2. The number of columns here is 4, and the number of rows here is 2. They don't match. The number of columns in the first matrix does not equal the number of rows in the second matrix. So therefore, the product is undefined. So let's take a look, before we look at determinant, let's take a look at some examples here where we're multiplying. Let me show you number 12, actually, before I move on to matrix operations. Screen is frozen. Let me close that out for a second. Bring that down and then go back to it. There we go. Okay. So let's look at number 12 here. I want to show you something. So it says, let A be this matrix and B is this matrix. And it says, solve the matrix equation 5A minus 2B equals 3X. And we're solving this for X. So what I'm going to do, I'm going to show you. I'm going to take this equation and I'm going to first start off by solving the equation for X. And then I'll work with the matrices, okay? So 5A minus 2B equals 3X. If we solve this for X, we can divide out by 3. I'm going to divide the whole thing by 3. So this ends up being X equals 5/3 A, because it's 5 over 3A, minus 2/3 B. So in other words, all I have to do to get the solution for X is let this matrix, plug it in the calculator for A, plug this one in for B, and then multiply 5/3 times this matrix minus 2/3 times this matrix. And whatever I get, that's my answer. So let's do that. I'll go ahead and show that. All I did was take that given equation and I solved it for X because they want me to solve for X. Okay, so I'm going to actually now get X by plugging in this into my calculator for these matrices. So I'm going to press second matrix. I'm going to edit matrix A. This is a 1, 2, 3 by 2. 3 by 2. So I've got -7, 6, 7, -5, 7, -1. Okay, so I've got A. Now I'm going to get out of that. And I'm going to press second matrix again and edit B. So I went over to edit and I'm going down to B. This is a 1, 2, 3 by 2 also. So -5, 5, -7, 6, 8, -6. Okay. All right, we're going to get out of that now. Press second, quit. And now let's type on our screen 5/3, 5 divided by 3, matrix A, minus 2 divided by 3, matrix B. All I did was type using my regular division symbol, 5 divided by 3, and then I went second matrix to select A, and then minus 2 divided by 3, and I selected B. I'm pressing enter there, and it gives me some nasty decimals, which I don't want. So I'm going to press math. Frac is highlighted first. I'm going to press enter to select it. And what the calculator is going to do now is take these answers and put them in fraction form. And there we have it. Okay. And it says type an integer or simplified fraction for each matrix element. This will be our answer for each matrix element. Okay. And of course, the solutions are at the back. If you want to see that we got the same answers there. Okay. All right. Number 13 and number 14 is asking us to multiply. I'm going to show you this on the calculator as well. So this is a 2 by 2, and this is a 2 by 2. So the products AB and BA are both possible because they are the same size. So whether I switch it or not, I'll get the same number of columns here. It will match the same number of rows here. So AB is possible, and so is BA. So let's actually plug that into the calculator. We can save us the work time. Let's press second matrix. Let's edit A first. It's a 2 by 2. So we've got -7, -1, 0, -3. And then let's go second quit and go second matrix again, over to edit and down to B, 2 by 2, -3, -8, -5, 5. -3, -8, -5, 5. Okay? Sorry about the glare. So we've edited both in. I go back to my home screen by pressing second mode to quit. And then I need to just pull up A times B, get that, and then B times A. So second matrix, select A. One is highlighted already. Just select it by pressing enter. And then press second matrix again and go down to B and press enter. A, B. We've got 26, 51, 15, -15. And then BA, second matrix, B first, and then second matrix, A. You can see how the order matters: 21, 35, 27, -10. And the reason it matters is because for the first one, you use the rows and then you multiply it to the columns of the second. So if you flip it, then that ends up meaning that you use the rows of B this time and the columns of A. So it ends up being a different matrix. Okay. Number 14, you would do something similar. This is a 1, 2, 2 by 1, 2, 3, 4. And this is a 1, 2, 3, 4 by 2. So this time, when you plug these in, it's possible that one of them won't be able to be found. Let's take a look at it so you can see. So I'm going to press second matrix. I'm going to edit A. That is a 2 by 4. So it's -3, 10, 6, -8, 3, 8, 8, 7. And then I'm going to go to matrix B, go over to edit and down to B, a 4 by 2, -2, 6, 7, 5, 5, 10, 4, 9. Uh-oh. Okay. All right. So we're done editing. Just double check, make sure our numbers are good. All right. Get out of that. Now we press A times B. We press second matrix, select A, and then second matrix, go down and select B. There our answer is being because the rows, or sorry, the columns and the rows match. So the size ends up being a 2 by 2, 74, 20, 118, 201. And then for BA, let's see if that's possible. Second matrix, B, second matrix, A. And it is. It's way bigger. It ends up being a 4 by 4, much, much larger. Okay? I'm not going to necessarily write that. All right. Let's see what's the last couple topics here, and I think we'll be done. Let's see here. Kind of gone a little longer than I planned. All right, determinant of a 2 by 2 matrix. So sometimes we want to know more about a matrix. Sometimes you'll be asked to find the determinant. It is denoted by basically their cross products, the differences between their cross products. We also say that the value of the second order determinant is simply A1 times B2 minus A2 times B1. So it can be called the value of the, it can be said to be the value of the second order determinant. It's called a second order when it's a 2 by 2 here. Again, the calculator can find this for you, but a 2 by 2 is actually pretty easy to find. It's just the cross products and then the difference between them. When it gets a bit bigger, then that's where you may want to let the calculator do it for you. I'm going to show you that too. Here's an example by hand. It says evaluate the determinant of the following matrix. So it's where you do the cross products. 10 times 5 minus 9 times 6, or 6 times 9. So 50 minus 54 gives us a -4 determinant value. Why they may ask for the determinant, there's really not much you would do with it right now, period, really, in this class. But if we were studying beyond, if we were kind of getting more into matrices, if this was a class devoted more to matrices, we would kind of be introduced to something called Kramer's rule, and it would involve more with matrices and kind of give you more information as far as why the determinant even matters. But right now, it's just figuring out the determinant. It's nothing that you need to stress yourself about. This class doesn't dig that deep into matrices beyond this section here. And you don't talk about matrices at all in 1720. And I'm trying to remember in calculus, do we mention anything about it? No. So, yeah, it's not, if it was like financial math or we were in finite math or business calculus, maybe, but it's not referenced beyond this. Here's another one. 4 times -8 minus, and remember this, the formula calls for it to be minus. And then, I think I messed up a bit here. There should be a negative sign with that 5. Yep. Let's put that one in the calculator. I'll do one in the homework. When it's a 3 by 3, you're trying to find the determinant of a 3 by 3. That is, in other words, the definition of a third order determinant. Way more involved. Okay, you can see how all that is kind of looking a little like what? But here is where it comes from. So you take the first column values, and you multiply it to a 2 by 2 array, I guess you can say, using the elements that correspond to it. So if I'm using A1, then I use the other B2, C2, B3, C3. When I'm using A2, I use B1, C1, B3, C3. And then A3, I use B1, C1, B2, B2, C2. Okay? But I would not ask you to do that by hand either. We will look at the calculator for that as well. But you can see that worked out with an example or two here. Okay. All right, so let's look at a few here from the homework and then I'll wrap this up. So look at number 15. It says evaluate the determinant. So I'm going to I can do this by hand. 2 times 5 minus 1 times 1. So 10 minus 1, we get 9. I do want to verify this in the calculator so you can see how the calculator does it for you as well. So I'm going to let this be let this matrix be matrix A, call it A. So I'm going to put it in A. So I'm going to put second matrix, press second matrix on my calculator, go over to edit, and this is a 2 by 2. Putting in 2 by 2. So this is 2, 1, 1, 5. Okay. Now I'm going to get out of that and I'm going to press second matrix and I'm going to go over to math. And determinant is the very first item, number 1. So I'm going to press that, and then I'm going to tell the calculator to find the determinant of matrix A, where I put the matrix at. So I press second matrix again, and I select A. And it's 9. Okay? No matter the size. Remember, determinants is for a square matrix, 2 by 2, 3 by 3, 4 by 4. Okay? Beyond 3, it gets very crazy. We don't even have the formula for it provided to us here in this section. But I don't even know if you're asked anything beyond a 2 by 2. Okay, yeah, there is one more question here that asks you to find the determinant of a 3 by 3. And the formula is on the notes, but we can use the calculator, okay? 2 by 2 is really straightforward. It's pretty easy. -3 times -2 minus 6 times -1. So that is 6 plus 6, which is 12. Okay. And this last one here, let's do this one. We're going to definitely use the calculator. This is a 3 by 3. We're going to let this matrix be A. Okay. So I'm going to put that in for matrix A. I'm going to press second matrix, go over to edit. It is a 3 by 3. So I've got 4, 5, 0, -5, 4, 0, -3, 4, -5. I get out of that by pressing second mode. Sorry about the glare. And then I press second matrix, go over to math. Determinant is number 1. And then we put this matrix in matrix A. So I'm going to tell the calculator to perform or find the determinant of matrix A by selecting A. -205. And we can, of course, verify that. Remember when I sent out the work, the solutions are at the back. Okay? All right. That is all I have for matrices. And I will see you all next time. Enjoy your week. Have a good weekend.